Jai Hind, welcome to class of Analog and Digital Communication. We are covering Unit 4, which is Digital Modulation. As talked before, why do we need to switch from analog form of communication into digital form? Although all the signals available in nature are analog in form, like the flow of wind, the temperature rise, humidity, all the signals, the audio communication that we do every time. So all the signals available, most of the signals available in nature are analog in nature, but there is a need for conversion of analog signal into digital because digital signal consumes lesser memory. It is more immune to noise. The coding techniques available are applicable on digital in a better way. So there are n number of reasons that make us switch from analog to digital communication, right? So this is a picture that shows how analog signal, this analog signal, which can be represented as a function of time, and when we convert it into digital format, that is usually a binary representation of bits that is in the form of zeros and ones. So the modern computers or the equipments that we use in today's world, they do communicate in digital manner, right? So if we take example of a simple internet system, right? So the data entry that we do manually, what we enter, that is communicated to the other end in the form of digital manner only. Whether we talk of the mobile communication, the internet facility, or any other kind of communication that we do in today's world, most of the data gets converted from analog into digital format, and then that is transferred or transmitted. And at the receiver end, it is again converted back into its original form and is received by the intended recipient or the destination, which is usually in human understandable form. So about the classification of digital communication, there are three basic techniques that we do talk about, that is amplitude shift keying, frequency shift keying, and phase shift keying, right? The first of all these three is amplitude shift keying. What is amplitude shift keying? Here the amplitude of the resultant output depends on the input data, whether it should be zero level or a variation of positive and negative depending upon the carrier frequency. So first thing that I should clear it here is the digital data that we have available in form is usually binary in nature, right? Here we do consider that the input information or the message signal is already in digital format. If not, the first step is to convert that data into digital format, which we have discussed in detail in our unit 3. That includes steps like sampling, quantization, and encoding, right? Just to recall, if I want to convert my analog signal into digital, the first step is sampling, which will convert a continuous in time, continuous in amplitude signal into discrete in time. Followed by sampling, we perform quantization, which will discretize the amplitude level. Now we do have time and amplitude both in discretized form. Third thing that we do is encoding, that is binary representation of my data. After binary representation of my data, what do I receive is binary bits. So let's suppose I do have my binary data in the form of ones and zeros. And now for digital communication, what kind of carrier I'll require? That is a big question, right? So as I know, for digital communication, what is digital communication? When my message is available in digital format, right? This is the very basic kind of classification that we do. What is analog communication? Where my message signal available is analog in form. Digital, where my message signal available is digital in form. If it was analog, first what we did is we've converted into digital. Second question is what kind of carrier that we use for digital communication. So for digital communication, it is so obvious that the message signal is binary in nature, and the carrier that I use will be a high frequency sinusoid. Now here, how do I classify that this is a high frequency wave as compared to this? So one thing that I consider here is corresponding to the bit duration, my carrier frequency must be too high. Now how do I consider what is bit duration? Time taken by a single bit in a communication channel to propagate, right? So that is the bit duration, which is usually represented by TB. Now I have to assume a kind of carrier wave which will follow multiple number of time cycles in that TB, right? Then I can consider that my carrier is much higher in frequency as compared to the message signal, which is binary in form here. If it would have been an analog signal, this picture clearly depicts that when one cycle of my message passes, there are multiple cycles of carrier. But in case of digital communication, as my data is binary in nature, I have to take care of one thing: in a bit duration, more number of cycles must be passing, right? So if I talk about the basic definition of what digital communication is, when I alter the characteristics of this high frequency carrier wave with respect to the binary input, that kind of modulation will be digital modulation. Now my carrier is a kind of sinusoid, it is a continuous wave. So I can represent it with, again, a sine omega t. So what are the factors that are available for change here, for modulation here? Factors available are amplitude or the angle. So if I alter the amplitude of my carrier wave with respect to the binary input, then that kind of modulation is called as amplitude shift keying. If I'm going to vary the frequency of my high frequency carrier wave with respect to the instantaneous value of my binary data, here my instantaneous value will not be according to this voltage signal. It is a binary sequence, right? So according to the binary input, if I vary the frequency, that will be called as FSK, frequency shift key. If I vary the phase of my carrier with respect to the message input, then that will be called as phase shift key. So in amplitude shift key, it is a type of amplitude modulation which represents the binary data in the form of variations in the amplitude of a signal. True? Following is the diagram. Let's see. If I represent bit 1 with some positive voltage and bit 0 with some negative voltage, this is the representation for my input binary sequence. So whenever bit 1 appears, the carrier will have the amplitude similar to that of the carrier itself, and when there is bit 0, there is no amplitude here. You can see that, right? When bit 1 appears, it will have the amplitude. When bit 0, no amplitude. Bit 1, yes. Bit 0, no. Bit 1, yes. Bit 0, no. So this is how I can represent my amplitude shift key wave, right? So this is the output of my amplitude shift key. Now if I talk about the generation, how can I generate such wave? What kind of output do I need? For if ST represents my output wave, where my BT is binary input, my ST will be equal to the carrier. If I represent my carrier by CT, it will be CT for binary input 1, and it will be 0 for binary input 0. So if with BT I represent my message signal, if with CT I represent my BT would be a sequence of bits, and CT would be simply my sinusoid carrier. So simply my output is equals to CT when I give input which is binary 1, and when I give binary input 0, I should be getting 0. So what kind of modulator comes to my mind for designing such system, for getting such kind of output? So one of the input will be, to a modulator, one of the input is a pure sinusoid wave, that is a carrier wave. Another input here would be the message signal. Here the message signal I will not provide directly bit 1 or bit 0. I'll pass it through a level converter first, right? Because what do I need? I don't want my binary. See, this could be a product modulator which is represented here with the form of a switch which get closed and open at every bit duration. Because when do I have to pass the output? At every bit duration, right? This is how my receiver will recognize at what timing it should read it as individual bit, at every bit duration. So the closing and opening of the switch will also be decided by the closing and opening of with the bit duration, right? TB, which are represented by TB. But I don't want my carrier to get simply multiplied by bit 1 or 0. Corresponding to bit 1, there should be some voltage value that should be multiplied, and corresponding to bit 0, there should be 0 voltage value, that is, switch should be open, right? This is what I want, because for such input, if this is the carrier, ASK output will somehow look like this, right? If this is my BT, this is my CT, this is how I want my ST to be, right? For such system, I want this kind of arrangement. So this is a continuous carrier which is going. For bit 1, I transmit. For bit 0, nothing. So for bit 1, when the switch closes, what we pass is simply carrier. For bit 0, switch is open, and what do we pass is nothing. Or we can say at every bit duration, when the switch closes, for bit 0, what voltage we pass? Close to reference, which is 0. And for particular that bit duration, what we get is this. Again, switch closes at next bit duration, and if it was bit 1, what do we pass is, suppose, this voltage level, and again for bit 0, nothing, right? Now, of course, at transmitter we do have a band pass filter, and that will give you ASK output, which is band limited, right? The carrier, let's go through it. The carrier generator sends a continuous high frequency carrier. The binary sequence from the message signal makes the unipolar input to be either high or low. The high signal closes the switch, allowing a carrier wave. Hence, the output will be carrier signal at high input, as discussed. When there is low input, the switch opens, allowing no voltage, right? So what we are actually performing? We are managing the switching corresponding to the bits. If bit 1 passes, switch closes. If bit 0 passes, switch is open. And like that, for bit 1, carrier passes as it is. For bit 0, as the switch is open, there is no voltage, right? The band limiting filter shapes the pulse depending upon the amplitude and phase characteristic of the band limiting filter or the pulse shaping filter. True. Now, after generation, let's talk about demodulation. So this with this diagram, I have tried to show an asynchronous ASK demodulator. We'll come back to this. Let's see what is an asynchronous ASK demodulator. First of all, as the word says, asynchronous. Asynchronous means we do not depend upon coherence here, right? We are not dealing with that at receiver we should be having a coherent detector or an oscillator which will be generating the wave coherent in phase and frequency to that of which is used at transmitter. No, we do not need such kind of system. This is a completely independent kind of system which is asynchronous in nature. It does consist of a rectifier, a low pass filter, and a comparator, right? Input to this will be ASK wave. ASK somehow looks like this. This is the input to my rectifier. We know the job of a rectifier, right? We know the job of a low pass filter, also that of comparator. Let's see how it works. Finally, what do I want is retrieve back my message signal, right? Let's see how it works. The modulated ASK is given to the half wave rectifier, which delivers a positive half output. We know that half wave rectifier passes output at positive half cycle, and for the negative half cycle it remains open, so it doesn't passes anything, right? This is what we want. Now, so my half wave rectifier, for it will act for the positive half cycle, for the negative half cycle it doesn't work. So when this goes to low pass filter, LPF suppresses the higher frequencies and gives an envelope detected output from which the comparator delivers a digital output. Now what my low pass filter will do, my low pass filter will read these values, right? This value, this value, this value, right? Now comparator is a kind of circuit which will compare the input value with some available threshold or reference value, and if it finds that, if it has some reference value, suppose 3 volt, this is at 5 volt and this is 0 volt, what it will do, it will compare this 5 volt with 3 volt, and if this is higher it will read it as bit 1, and if this is lower, 1 is lower than 3, it will read it as bit 0, right? This is the job of a comparator, to compare the input value with the already available reference and correspondingly give some result. So that was about asynchronous detection. Now if I talk about synchronous detection, how ASK can be demodulated using a synchronous detector, then this will have some information about the carrier which was used at the transmitter. How it works, like here the output input to the detector will be ASK modulated wave. It first passes through a square law detector. What's the job of a square law detector? It will read the voltage values, right? It will read the voltage values. Here it has some voltage value, here 0, here, right? And it will pass it through a low pass filter. Then again it will pass it through a comparator, and with the help of a voltage limiter the final output is derived. Let's see how it works. The ASK modulated input is given to the square law detector through. Square law detector is one whose output voltage is proportional to the square of the amplitude modulated input voltage. Now square law detector will give output in a way so that the output is equal to square of the input, right? This is how passive elements used in square law detector works, right? Squaring the value. Now what the low pass filter will do, it will minimize the high frequencies, true, and the comparator and the voltage limiter help to get a clean digital. The job of a comparator and voltage limiter is to extract out digital output from the continuous input, right? So this is how my synchronous ASK demodulator works, right? So this concludes my ASK. What is ASK? ASK generation and ASK demodulation. Now if I talk about FSK, which is the next kind of digital modulation technique, which is also called as frequency shift keying. Let's see. What is frequency shift keying? FSK is the digital modulation technique in which frequency of the carrier wave is varied according to the digital signal changes, right? Whatever digital signal input we have, corresponding to that, if we vary the frequency of the carrier, that kind of modulation will be called as frequency shift keying. So it is a variation of frequency modulation itself, right? The only difference it has from frequency modulation, as we have studied in analog communication, is here the input message signal is binary in nature and carrier is high frequency sinusoid, right? And what kind of results are we expecting? Now here the frequency of my carrier wave will be varied corresponding to the input message. That means I am going to get the frequency value as per the binary input, and I do have two variations of input, either bit 0 or bit 1. So corresponding to bit 0 I'll have a frequency value, and corresponding to bit 0 I'll have a frequency value, and corresponding to bit 1 I'll have another frequency value, right? Here the output of a FSK modulated wave is high in frequency for a binary high input and low for binary low input. We can take the vice versa case as well, right? This is a assumption only, like I can consider corresponding to bit 1, I can assume lower frequency, and corresponding to bit 0 as well, I can assume higher frequency. That totally depends. The logic is to assign a frequency value corresponding to the binary bit input. So binary 1s and 0s are called as mark and space. 1 is called as mark and 0 is called as space frequency. The following image is diagrammatic representation. See, for bit 1, there is some increase in the frequency. For bit 0, there is some decrease in the frequency. For bit 1, again increased frequency, bit 0 decrease, bit 1 increased, bit 0 decrease, bit 1 increase. It will be like, let me draw, this will be then clear in a better way. Like, if let me take 3 bits only for ease. Let's consider corresponding to each bit duration, there were 2 cycles of carrier which was normal carrier frequency, right? So now this was my BT, this being my BT, this being my CT. Now corresponding to bit 1, if I consider, my frequency will raise to twice the value, and corresponding to bit 0, it will go to half. Or you can take any value. Here if it is x, it could be 2x, it could be x by 2, or here it could be 3x and x by 3, x by 4, any value. So now for bit 1, I may choose here to be 4 cycles, and corresponding to bit 0, instead of 2, maybe 1 cycle. Corresponding to bit 1, 4 cycles. And like that. And corresponding to bit 0, if earlier there were 2 cycles, I may choose 1 cycle on likewise, right? So corresponding to bit 1, there is one frequency value, corresponding to bit 0, there is another frequency value, and we have named it as F1 and F2. Now how to generate such kind of output? If I talk about the block diagram of such generator, this is how the block diagram looks like. Here for I have to use 2 frequencies, so 2 oscillators I'll be using. These are the 2 oscillators. This is an arrangement which will act as a switch. Another input to this modem, this module, will be the binary sequence, that is my message signal. So carrier I am providing here, carrier with 2 distinct frequency, which are F1 and F2. F1 and F2 corresponds to bit 1 and 0 in the output, right? So these are the inputs, and another input is my message signal, and what I get is the output. How it works? We do have 2 oscillators with a clock and an input binary sequence. When the clock works at every bit duration, right? This is important. When do I consider 1 bit is passing, another when do I have to consider, like otherwise I'll go with complete set of 1s continuously, right? So it has to be precisely synchronized with the bit duration, the clock sequence. The 2 oscillators producing a higher and lower frequency signals are connected to a switch with an internal clock, true. To avoid the abrupt phase discontinuous of the output waveform, during the transmission of the message, a clock is applied to both the oscillators internally, true. Clock is applied to both the oscillators internally. The binary input sequence is applied to the transmitter so as to choose the frequencies according to the binary input, right? So sorry. So as to choose the frequencies accordingly. Frequency, what frequencies we are using? F1 and F2. So here F1 we are considering close to F2, but bit rate Fs must be much lesser than F1. Here again I have to take care of one thing, that my binary bit should be provided in such a way as input so that the bit duration is always much higher than that of the carrier frequency. Right. Now if I talk about how such generated FSK can be demodulated, so let's talk about the demodulation part. What other kind of types of FSK demodulators we do have? There are different methods for demodulating an FSK wave. The main methods of FSK detection are asynchronous and synchronous. Again, asynchronous means here my receiver will have no knowledge about the transmitter, and in case of synchronous detection, it should have some knowledge about the transmitter, right? The synchronous detector is coherent one, while asynchronous is a non-coherent one. Let's see. If I talk about the asynchronous detector, it consists of two band pass filters, two envelope detectors, and a decision circuit. See, here I'm giving this kind of input I give, which is FSK. It passes through two band pass filters. I'll set its frequency, one of the frequency to F1, one of the frequency to F2, so that it passes this frequency only. If I consider this as F1, this is F2, through the first path, only F1 frequencies will pass through. This only F2 frequencies will be passing. And here the envelope detector, what it will do? It will just read the peak values. And here the decision circuit will decide whether this is bit 1 or 0. So we know that this will be working when I have this part going. So at this point of time, it can give decision 1. For this point of time, this will come into loop and this will be giving decision as bit 0, and likewise it works, right? FSK is passed through two band pass filters tuned to space and mark frequency. One is tuned to F1 frequency corresponding to bit 0, and mark frequency corresponding to bit 1. The output of these two band pass filters look like ASK signal. True, output will look like ASK. Why? Here it will be like this, and no. Here it will be no, then this, right? True, because for first bit duration this will pass, for second bit duration this will pass. The signal in each envelope detector is modulated asynchronously. The decision circuit chooses which output is more likely and selects it from any one of the envelope detectors. True. It also reshapes the waveform. If some distortion abnormalities has come, it will be removed to a rectangular one. After asynchronous, let's talk about synchronous FSK detector. It consists of two mixers and a local oscillator circuit and two band pass filters and also a decision circuit. Let's see. As mentioned, two mixers or product modulators, two oscillators, two band pass filters, and a decision circuit. How it works? The FSK signal input is given to two mixers with local oscillator circuits. These two are connected to two band pass filters. True. One of the input is FSK. Another is locally generated carrier. So this is a kind of synchronous detection. That means coherent detection. That means here my receiver will have knowledge of the transmitter. That it'll have the oscillator which is generating same frequency as generated at the transmitter, which are my F1 and F2 frequencies. And we do have two band pass filters which is tuned to pass my F1 and F2 frequencies. The window is kept like that. These two are connected to two band pass filters. These combination act as demodulators, and the decision circuit chooses which output is more likely and selects it for any of the detectors. The two signals have a minimum frequency separation. True. For both the demodulators, bandwidth of each of them depends on the bit rate. True. This synchronous demodulation is bit complex, right? It should have prior knowledge, so this is bit complex, right? So this is what we have discussed today. Two variants of digital modulation, which is my amplitude shift gain, its definition, its waveform, how it is generated, that is modulators and demodulators. Secondly, about frequency shift gain, what is FSK, how it waveforms looks like, then about the modulators and demodulators. That's it for today. These are the references I've used.